4.1, maxima and minima. So the concept is pretty easy. We'll be finding, let me just sketch a couple graphs here. Right, so let's say we have a function like this, right, and here we have an absolute minimum, right, at this point right there. So we'll be finding, points like that. So that'd be absolute minimum, and a point like this will be absolute maximum. Okay, so let's start with an example. And also, well, there is another thing to it, because we'll be finding those points on a certain interval, right? So this is a parabola that, if it was just a regular parabola, that would go to infinity, right? To the positive infinity in both cases. But well, most of the time we'll be just focusing on a certain interval. Right? So this could be, I'm not sure, from -2, say, to 2. Okay, so we'll be finding maxima, minima on a particular interval. Okay, so let's do an example. Let me actually erase this. Okay, just to have more space. All right, so example 1. And goes like this. So given f of x equals x squared minus 2x. And yeah, we have a specific interval. So interval is from 0 to 4. And yeah, find absolute minimum and absolute maximum of the function. So find, maybe I'll just write extrema, absolute extrema of the function. Okay, so let me maybe draw. I don't want to draw that specific function x squared minus 2x. I just want to kind of explain what's happening. So let's say we have something like this, right? So we have a function that looks like this, and it's actually, right, will be, in this case, right, that interval will be from -1, right? So this is -1, and then here, I'm not sure what this is, maybe 2.5, 2.5. Right, so when you look at this, there are a couple possibilities for those extrema, right? For those maxima and minima. So one of the possibilities, let me take a different color, would be here, right? So that's one of the points that could give you that maximum or minimum. Then there is this point, right? And then there's this point, right? So 1, 2, and 3. So basically, right, what we could do, we could take all those x's, right? We don't know what the x here is, right? What the value of x is for this point, but we know the value of x for this and this. Right? So the only thing we basically need to figure out is the x of that point. Right? Because once we have it, we can take all those 3 x's, 1, 2, and 3, and plug them into the original function and find what the highest and what the lowest numbers are. Anyway, so, and again, let me erase this because that's not the proper graph, that's not the real graph of that function. And actually, let me redraw a parabola. Okay, I hope you remember that when I have a parabola, right, so, or a curve, then this would be my minimum, right? And you see that the slope of a tangent line, so we have a tangent line here, looks like this. So you see that the slope of that blue line, right, is 0. Slope, and is the first derivative. Okay, so what we'll do, we'll take a first derivative of our function, make it equal to 0, and see what that x is, right? So we're looking for this x, for the value of this. Okay, and again, let me erase this, because it's not really relevant. Okay, so take a derivative. Right, so it's x squared minus 2x. So derivative of that first term is going to be 2x. Derivative of the second term, I'm here. I'm taking derivative of x squared, 2x. Derivative of negative 2x is negative 2. Okay, now we're going to make it equal to 0. Right, it's because, right, we're looking for x where slope is equal to 0. So I have 2x minus 2. So 2x minus 2 equals 0. Right, we're solving it for x. So 2x equals 2. X equals 1. Okay, so for this x equals 1, right, slope will be 0. So this could be right, minimum or maximum. We don't know. So so now we have 3 points, right? So we have those endpoints, 0 and 4, and then we have that x equals 1. Right? So those extrema could occur for those 3 different x's, 3 different points at 3 different points. Yeah, let's write it down. So max, maximum, and minimum can occur at 0, 1, or 4. Okay, yeah, so now to figure it out, we would just simply do f of 0, f of 1, and f of 4, right? Those 3 x's, 3 suspects. Okay, so let's start with f of 0. So I'm just taking, right, I'm taking that 0 and plugging it into the original function, and this one. Okay, so it's going to be 0 squared. Right, I'm just simply figuring out what the, right, so I have those 3 x's, 1, 2, 3, and figuring out what the y's are for those 3 x's. So I have 0 squared minus 2 times 0, so that's 0. Okay, so for 1, we have 1 squared minus 2 times 1. So we get negative 1. Okay, and the last one is f of 4, so plugging in 4. So we have 4 squared minus 2 times 4. Okay, so this is 8. Okay, so you see what's happening, right? So we have, what do we have? We have 0, negative 1, and 8. Now obviously negative 1 will be our minimum, and that 8 will be the maximum. Okay, so this negative 1 obviously is minimum. Then we have 8, and that's maximum. Okay, so let's let me draw a graph. So you can see what's going on. Okay, so we know that interval, right? That interval I was from 0 to 4. Right? And those two numbers, those two x's are included, right? By the way, this is not a point, right? This is interval from 0 to 4. Okay, so now it's a parabola. Maybe, how should we do this? Okay, let's say this is, I'm going to mark this as 1. Maybe not. Let's see, what is the best choice here? Yeah, how about this? So 1, 2, 3. Extend this and need to go all the way to 4. So 1, 2, 3, 4. Okay, so we know that for 1 we have negative 1, 0, 0, right? 1, negative 1, so here. Then I also know that for 4 I get 8, right? So this is 4 and this is 8. And the drawing, of course, is not in scale. So 4, 3, 2, 1, 4, and 8. Okay, so the graph looks like this. Right, and it stops here. Okay. So now, yeah, let me show you how I got those points, right? So the first, right, is that 0, 0, right? So I'm plugging in 0 for x, I'm getting a 0 for y. So that's how I got this point. Right, so for 1 I get negative 1, right? So you see that for 1 I get negative 1, for 4 I get 8, right? So negative, so this one is 1, negative 1, and this one is 4, 8. Okay, so you see, right, this is the maximum, and that point here obviously is the absolute minimum. Okay, so let's look at the definition of those extrema. So definition. So we have let f be defined on interval I I have more space here, interval I containing number c containing c. Now if f of c let me actually make it, because minimum, so this is definition of minimum, so let me make it blue. So if f of c is less or equal than f of x, no, I need white. for all x's in that interval then f of c is the absolute minimum. And let me sketch a quick example. Right? So we have some function. Okay, could be like this, and then, well, yeah, this is the number c. Right. So obviously, right, you can see that not. Yeah, let's mark that interval somewhere. Right. So the interval is, say, from here. And an interval I to there. Okay, so then obviously, right, so this is the, if that is c, this is f of c, and that f of c is lower than any f of any x, right, on that interval, right? I hope you can see that. Okay, so so this was absolute minimum. For absolute maximum, let me maybe write it this way. It's absolute minimum. Okay, and then for absolute maximum, right, the definition is the same. Absolute maximum. And the only difference is that f of c is less or equal, right, than any other value of the function. F of c is greater or equal than any other value. Okay. Yeah, maybe a quick sketch, right, similar to what we had before. Okay, so again, right, so we have that point C right there, and that interval could be, right, from here maybe to there. So you see that, right, so that f of c is higher than the value of that is bigger than any other value of the function. Okay, so absolute minimum, absolute maximum. Okay, so I'm not going to get too deep into those, right? So now the next thing, I want to talk quickly about this local maximum, local minimum. So it's local or relative. I'm just going to quickly explain the concepts. So relative or local extrema. Okay, so let's actually graph a specific function. So example 2, and f of x equals x to the third minus 3x squared. Okay, so we need to locate those local extrema. Okay, so here's the graph. So it goes through the origin, goes through the point 2, -4, and these are those local maximum and minimum. And here's the graph. Alright, so it goes like this. Let me redraw it. That particular point. Okay, so local minimum, local maximum, and I hope you understand the idea, right? So it's that highest point, right? So that origin 0, 0, right? It's a highest point, highest value only for a certain environment, for a certain neighborhood, right? So local, and this one is the local minimum. Oh, I already have it here. Anyway, so this one is the local maximum, right? And this one is the local minimum. And you see, right, that there are numbers, that there are values that are higher than that, right, than that 0, and lower than that -4. So this was local minimum. Okay. Yeah, another concept related to those maxima minima is critical numbers, right? So critical numbers are basically numbers or x's where those absolute or local maxima and minima could occur. Okay, so critical numbers. And yeah, when we're trying to locate those maxima or minima, right, our first step will be to locate those critical numbers. And the definition is so let f be defined at C and so function is defined at that critical number at C, and then if f prime of C, let me write it here, right? So if we have that horizontal slope, or if f is not differentiable, at C, so the function is defined, right? But there's no, so there is like a hyphen there, right? There is no derivative at that C. I'll show you in a moment how that is possible. Then that C is a critical number. So then C is a critical number. Okay, so when the derivative is equal to 0, right? So we know that situation, that case. Okay, so we have a graph like this. So that's our C. And you see that if I have a tangent line, right, then that slope or derivative is equal to 0. Okay, and that other case where the function is defined and that C, we'll see examples, but there's no derivative, right? So when we have that point, right, so the absolute value was one of those examples, but here's another example, right? So at this point, at that tip of that graph, derivative doesn't exist. Right? So this is that C, and derivative doesn't exist. Okay. Yeah, let's make another comment. So not every critical number is an extremum. Okay, so typical example for that would be a cubic function. So let's look at one. So example 3. It's not x to the third, it's just example 3. Okay, so consider, let's look at f of x equals x cubed. Derivative would be just 3x squared. Okay, so 3x squared, and now we make it equal to 0. So to find that critical number, we take derivative, make it equal to 0. So we have 3x squared equals 0. So x equals 0, right? So technically, this is our critical number by definition, but it's not going to give us a maximum or minimum. So this is a critical number. Let's make that comment. And quickly graph here, just to show you why this is not okay. So here's the graph of the cubic function, and you see that at that, if you graph it in Desmos or some kind of software, right, you'll see that the slope right there at the origin is actually 0, right? So the graph just flattens out. So this is that 0, 0. And then this point is not a maximum or a minimum, right? Even though that the tangent of the graph to that point, even though tangent line that's tangent to the graph at that point has a slope of 0, right? This is not a minimum or maximum. Okay. Okay, so let me give you a summary of what actually is going on. Okay, so we have candidates for extrema. Alright, so we have two types, right? The first one is the is the critical points. Let me maybe do it like this. So the critical points. So one is critical points. Okay, and the second one is the endpoints. Okay, so let's leave it like this, and let me give you an example. So example 4, a proper example where you actually calculate those, find those extrema. So given f of x 2x minus 3x to the power of 2 over 3. Okay, find absolute maximum and minimum. And that interval is from -1 to 3. Okay, so we'll start with finding those critical points, right? So that's the problem. So first find critical points. All right, so we have two types of critical points. The first one is when derivative is equal to 0, and the second one is where the derivative doesn't exist. So let me rewrite that function. So f of x is 2x minus 3x to 2/3. Right, so that's the exponent. Okay, so derivative. Maybe right, pause the video and try to find the derivative on your own. Okay, so it's not that easy, especially that second term, right? Okay, so I hope you did that. And when you take a derivative of that first, right? So I'm taking derivative of this and then of that. Okay, derivative of 2x is 2 minus derivative of 3x to the power of 2 over 3, right? We take that 2 over 3, put it in the front. So let's do that. Times 3. Okay, so let me, okay, so this goes here, and then I'm subtracting 1, right? Okay, so you see that 2/3 in the front, and now I have x, and we have 2/3 minus 1, so that's -1/3. Okay, so f prime of x, we have 2 minus, so now I have, right, 2/3 times 3, so that's just 2 minus 2, and now I have that power of -1/3, so that's 1 over that, and 1/3 is a cube root, right, of x. Okay, so I hope you understand. So that negative here made everything go down, right, to the denominator, and then it's spent, right, and the power of 1/3 is just a cube root of whatever, of x in this case. Okay, so we have the derivative. So to find the critical points, we make it equal to 0, and then we also figure out when this derivative doesn't exist. Okay, so we make it equal to 0 and then solve it. So it's going to be 2 minus, let's put that 2 in the numerator. Or actually it's not. So 2, 1 here, cube root of, not 3, cube root of x. Okay, 3 is here, and that equals to 0. We can simplify it a little bit by dividing everything by 2. So 1 minus 1 here, cube root of x. So we could solve it algebraically, right? It's not difficult. But let's just think about it. So yeah, the question is, how can we make it equal to 0, right? Especially, how can we make this equal to 1? Because 1 minus 1 would give us 0. And the answer is by plugging in 1 in here, right? So x equals 1. It's our first, well, I think it's the only solution. Okay, so if you want to solve it, right, so you just multiply it by cube root of x, right, and well, you get something similar. Anyway, yeah, so we solved it just by looking at it, thinking about it. So x equals 1. So this is our critical number, critical point, but there's also another one, and because for x equals 0, let's write it. So I'm just looking at this. I'm thinking, is there a number for which this is undefined, this doesn't exist? And yeah, there is, right? If you plug in 0, then I get in for x, you get division by 0, right? So that gives you something that's undefined. So for x equals 0, derivative doesn't exist. Exist. Right? So we have two critical points. Okay, so we have x equals 0. X equals 1. But we have a couple other points, right, there that could give us those maxima, right? And those points are over here, right? There's -1, these two, and 3. So let's list them. Let's list it as what could we? What do I have here? Candidates. Okay, candidates for extrema. Candidates for extrema. Okay, so we have what was it? Right, that we have that interval over here. So -1, 3. -1, 3. And then we have 0 and 1. And then we just go one by one and just plug it in. Right? So f, right, of -1. And I'm not going to show you this arithmetic, right? You can, hope you can. Well, maybe I will actually for that first, for -1. So I have, where's that original function? Maybe I'll write it here. So f of x. I think it was 2x. So it's equal here. 2x minus 3x to 2 over 3. Okay, so plugging in -1, right? So 2 times -1. And we have minus 3, then I have -1, and then power is 2 over 3. Okay, so now that power of 2 over 3, right? So what that means is I'm raising it to the second power and then taking a cube root. Right? So if I raise, you could do the other way around, right? You could take a cube root first and then raise it to the second power. Okay, so if you do that, I'm getting -2, and here I'm getting +1 out of this, and then multiplying by -3, so that's -5. Okay, so f of -1 is -5. Then you do the same with the rest, right? So f of 0, I have 0 here. And then we have f of 1. we get negative 1, f of 3. I just estimated it as negative 0.24. Okay, so maximum, where is our maximum? Maximum is actually that 0 here, right? This is the highest point. And then for minimum, we had that negative 5. Okay. Yeah, so let me show you a graph. Okay, so here's the graph of the function. Let me make it on the other page, actually. It's not enough space. Okay. Okay, so then we just mark this 1, 2, 3, and these units. And here. Okay, so we have a couple of points given, right? So for negative 1, we get negative 5. So negative 1, negative 5 would be here. Then we have 0, 0, I think, yeah, 0, 0. Then we have 1, negative 1, so here. Then for 3, we have negative quarter, 1, 2, 3, so somewhere here. And I think that's the graph is, yeah, the interval is from negative 1 to 3. Okay, so we go up here, and then we have that local minimum, right? And the graph ends right there. Okay, yeah, so this is 0, 0, so that's the maximum. Actually, let me make it, right? I was kind of making the maximum red. So here is the maximum point, my value is 0. Then here was the minimum. Negative 1, negative 5. Negative 5. And then we have, yeah, a couple other points, right? So this one was 3 and negative 0.24. Okay. Yeah, so maybe I'll stop this video and I'll make another one. I'll give you a couple of problems to practice.